How'd you like to listen to .NET Rocks with no ads? Easy. Become a patron. For just $5 a month, you get access to a private RSS feed where all the shows have no ads. $20 a month will get you that and a special .NET Rocks patron mug. Sign up now at patreon.netrocks.com.
Hey, Carl and Richard here. As you may have heard, NDC is back, offering their incredible in-person conferences around the world, and we'd like to tell you about them.
NDC Oslo will be May 21st through the 25th. Go to ndcoslo.com to register.
NDC Copenhagen is happening August 27th through the 31st. The early bird discount for NDC Copenhagen ends June 2nd. Go to ndccopenhagen.com for more information.
NDC Porto is happening October 16th through the 20th. The early bird discount for NDC Porto ends July 21st. Go to ndcporto.com to register.
And check out the full lineup of conferences at ndcconferences.com.
HTTP timeouts. Database deadlocks. In software, it's not a matter of if things fail. It's a matter of when. One mishap like this, and some valuable data is lost forever. And these failures occur all the time. But it doesn't have to be this way. Introducing N-Service Bus, the ultimate tool to build robust and reliable systems that can handle failures gracefully, maintain high availability, and scale to meet growing demand. For more than 15 years, N-Service Bus has been trusted to run mission-critical systems that must not go down or lose any data ever. And now you can try it for yourself. N-Service Bus integrates seamlessly with your .NET applications and can be hosted on-premises or in the cloud. Say goodbye to lost data and system failures and say hello to a better, more reliable way of building distributed systems. Try N-Service Bus today by heading over to go.particular.net/.NETROCKS and start building better systems with asynchronous messaging using N-Service Bus.
Hey, guess what? It's .NET Rocks. I'm Carl Franklin.
And I'm Richard Campbell.
We're getting all of these shows done so that we can go travel for a bit.
Go on adventures.
Going on adventures.
We'll do more shows while we're adventuring, too.
And we're going to be at Techorama in Belgium. And I believe you're going to .NET Developer Days 2023 in Poland, right?
Yeah, in Warsaw.
Warsaw?
I'll be there. I think I have the opening keynote, actually.
Yeah, that's cool.
I don't know for sure, but it's possible.
I won't be there, but if you want to check it out and you're anywhere near Poland in October, it's net.developerdays.pl.
Awesome.
It's a great conference. I went there a couple of years ago and I had a great time.
Yeah, we had a ton of fun there.
Yeah.
Okay.
Anyway, let's get right to the meat of it with Better Know Framework.
All right, man. What do you got?
All right. So this is a blog post by Eric Elliott, March 31st on medium.com. This guy has written a pseudocode programming language. I almost said Sudoku. A pseudocode programming language for large language models. And it's called Sudolang, Sudolang. See what he did there? Yeah. And so he's been using pseudocode to express ideas to large language models since GPT-3. However, up until GPT-4, it didn't work extremely well, but then he's working on it, and I haven't used it, but there's a whole bunch of statistics and stuff in there, and he says, here's some commands and some modifiers and examples, and it looks good. I don't know. It seems pretty complex.
I mean, isn't English a pseudo language in the first place?
You would think so. Yes. But I guess it's somewhere between a programming language and natural language. But
there you go.
But I thought the whole idea of large language models was to use language, right? I think that's what you're saying.
Right.
I don't know. I can't really judge it because I haven't really read through it. So I thought it was interesting and came across my desk. And since, we're in the hype cycle of GPT, large language models and all of that stuff, people are going to start dipping their toes in tools to make them more powerful.
Right.
So somebody should check that out and get back to us and let us know how cool it is.
It's all explorations at this point, but interesting ones.
It is certainly interesting. Who's talking to us today, Richard?
Grabbed a comment off of show 1809. This is one we did about microservices architecture with our friend Sean Wildermuth.
Yep.
Back in the fall of 2022. Bart Lanoy said, Carl, Richard, and Sean, thanks a lot for the show. These days you seem to be doing something wrong if you're not using microservices and Kubernetes.
Yeah.
It's like everyone forgot about the KISS principle, and I have this battle with almost every client. There's nothing wrong with a well-architected monolith or service-oriented architecture. And deploying a handful of services on Azure App Service or functions is minutes of work with minimal skill required. Only a small percentage come to the point where they need full-blown microservices architecture, and if you're Googling for it, you're not one of them. Listen, Bart, here's your solution. When the customer says, I would like some Kubernetes, please, you get a spray bottle, put a big logo on it that says Kubernetes, and you squirt it on them.
That's right.
And then if you're really smart, you say, no.
And I got to remind everybody that the KISS principle is, and I quote, you got to lose your mind in Detroit, Rock City.
But I really appreciate this comment from Bart just because it's like, listen, there's not one way to solve every problem.
Right.
And if you're determining a technology before you've architected an application, you are on the wrong path.
Right.
Like that's just a given. Let's look at the problem space first. Then we can talk about what we built.
Right.
So, Bart, thank you so much for your comment, and a copy of Music Code By is on its way to you. And if you'd like a copy of Music Code By, write a comment on the website at .netrocks.com or on Facebook. We publish every show there. And if I read your comment, I'll send you a copy of Music Code By.
And, you can follow us on Twitter. That's all cool. But it would be really cool if you followed us on Mastodon, because that's where all the cool kids are these days. I'm at Carl Franklin at techhub.social.
And I'm Rich Campbell at mastodon.social.
And send us a toot. We'd like to hear from you. And that brings us to our friend Michael Perry, who I was shocked that we haven't had him on .NET Rocks, but we did have him on the Tablet Show.
Back in the day.
So I guess everything just ran together in my brain. And
well, it's not like we don't see him at conferences all the time and so
all
forth.
The time.
Like he's part of the circle, but
we were roommates.
Embarrassingly, we never did this show.
For crying out loud at an MVP summit, weren't we? Weren't we roommates?
Yes, we were. We were roomies.
Yeah. We didn't choose to be. It was just like, hey, I know you.
Yeah.
So let me formally introduce Michael Perry. Software is math. Every class is a theorem. The compiler is the proof. And unit tests check our work. Michael Perry has built upon the works of mathematicians like Mark Shapiro, Pat Helland, and Leslie Lamport to develop a mathematical system for software development. He has captured this system in a set of open source projects, Jenga and Assisticant. I love that name. Assisticant.
Yeah, that was my daughter's name.
Oh,
she,
cool. What?
Yeah. Well, when so my daughter Kayla, whenever she
I
would
thought her
help
name was Assisticant.
No, but whenever she would help her mother out at a show, then she would ask, "Hey, can I come along and be your assistant?"
Oh, that's so cool.
That's great. I love that.
It's almost like something that goes in a squirt bottle for Kubernetes, isn't it? A little Assisticant.
Yeah, indeed.
Yeah. Well, anyway, great to have you on the show. And just your bio sort of sets the tone for what we're going to talk about here, doesn't it? This is really fascinating to me.
Yeah. And by the way, the other open source project is pronounced Jinaga.
Oh, what did I say? Jenga?
Yeah. Jenga. Yeah.
Jenga?
Yeah, it's not the tower of bricks that are going to fall down on you. It's much more stable than that. But,
Jinaga. So what is Jinaga?
Yeah, Jinaga is a platform for managing data in a distributed system. One of the great examples is in a mobile application. If you think about each mobile device being its own separate node within the network, then you can have your data on your mobile device, interact with it as a user, and then it kind of syncs up with the replicator, and you get that eventual consistency. So yeah, Jinaga is a way to turn your microservices, mobile applications, web applications into these small isolated nodes that eventually reach agreement.
That sounds interesting. And Assisticant is what?
Yeah, Assisticant is an MVVM framework that is based on the idea of dependency tracking. If you remember, Steve Sanderson's old Knockout library. Yeah, that's the same algorithm that it figures out what depends upon what, so that when something changes, it notifies the dependent.
Wow, and so you're talking large object models then?
I tend to use Assisticant for the smaller focused, like this is going to be a view model for just a single page, or even a composite view model with a page that has a list in it. Each one of those elements in the list is its own smaller view model. So that's what I tend to use Assisticant for. Not so much for the larger ones.
So some MVVM frameworks come with sort of communication tools of one kind or another, don't they?
Mm-hmm.
Yeah.
Yeah. A lot of times when you see MVVM, it's like, how do I implement iNotify property changed? And I'm like, well, let's take a step back.
Right.
Let's not try to implement the programming problem at hand, but instead try to specify the desired behavior.
Yeah, sure.
And then let the computer figure out how to give you that desired behavior.
Or we could just use Blazor.
That's true. Yeah. Blazor is fantastic.
Isn't it great? Just love it. All right. So, we're talking about how does this, incredible bio here that, that you've built this mathematical system for software development. And I guess your two projects that you talk about illustrate this, but, how does that align with the idea of immutable architectures?
Yeah. So this kind of goes back to, if you look at those mathematicians I mentioned there, Mark Shapiro, that first one.
Yeah.
He and his co-author Nuna Pragusha, basically published the very first CRDT specification. That's a conflict-free replicated data type. This is a mathematical object, that, has some amazing properties, in that, it will reach eventual consistency. So it will reach consistency as soon as all of the nodes have received all of the information.
Eventual consistency, because this doesn't come up often on .NET Rocks, but this is the idea that I have object A with a state, and when that state changes, eventually object B, that is some sort of replicant of it, is going to change, whether that's a database or whatever, eventually.
Yeah, exactly. Yeah, and what's really exciting about that, so you might have heard of algorithms like Paxos that are based on consensus. So these different nodes have to collaborate with one another. They have to chat back and forth in order to come to an agreement. Who's going to have the correct state. In the case of a CRDT, the way that the data structure works will guarantee that as soon as they all receive the same information, they are in the same state. They don't have to go through this extra
checks and balances.
Yeah. It's pretty cool stuff.
That is cool. Yeah.
Well, it's interesting to have this stuff as sort of solved models, right? Like there are exemplars or design patterns even of how you should build these kinds of problems. Like you should not invent a new implementation of eventual consistency.
Right. Yeah.
It's very easy to be wrong. It's very difficult to detect that you're wrong.
Uh-huh.
And it is a solved problem.
Yeah, it is. Yeah. It's very similar to what I was just saying about, write the specification and let the computer figure out the implementation.
Right.
Computers are really good at computation. They can take an equation, they can solve it, they can give you the correct answer. You give a human that same problem, they're going to make mistakes. But now if the human approaches that problem, but instead writes a specification, now what they're doing is they're giving the computer the equation. They're saying, I want you to produce a system that does this. Taking it back to CRDTs. One of the first CRDTs that Mark Shapiro and Nuna Pragusha published was TreeDoc. This is a CRDT that supports collaborative editing of text documents. So, so if you're familiar with Google Docs, Google Docs doesn't actually use this algorithm. It uses something else called operational transforms, which are known to have defects. But if they had used TreeDoc, then, basically by specifying, okay, these are the rules of the CRDT, computer, you come up with the implementation, then by using the mathematics of CRDTs, it would be able to come up with a correct implementation of collaborative text editor.
Michael, did your interest in computers and math sort of grow at the same rate, or was there a period in your life when you were all math and computers came after that?
Oh man, yeah, I think they pretty much did grow at the same rate.
That's cool.
But yeah, I've just always loved the mathematical side of software. I've always seen it as applied math.
That's a very unique place to come from for software developers, isn't it? Because, you get to experiment with both models at the same time.
Mm-hmm.
Yeah.
Yeah. And you end up with some really surprising results too. Some things that people don't expect to work. Like when I show people Assistant, it's like, well, yeah, it's a very simple idea. You write like a property getter, for example. Write a property getter, and if it's going to reach out and get values from other properties, then you know that it depends upon those.
Yeah.
So why not just have the computer watch while it's executing that and see what it does? And now you've just tracked your dependencies. And so whenever those things change, this property has changed. And so it's like, well, yeah, that makes sense. That follows logically one from the next. You've basically just told me a proof, that you're going to get the correct behavior out of a dependency tracking system. And then you actually, then here's an implementation of it. Let's run it. And it works. And it's like, it's magic. It's like, no, it's not magic. It's math. I just explained it to you.
Yeah. And very reliable math at that.
Yeah.
Of course, many of the original computer people were mathematicians. I mean, fundamentally, we're still all using von Neumann machines. And von Neumann was a mathematician. The question is, if he wasn't born in a day where there was no computers, would he have been a computer scientist rather than a mathematician? Like you didn't really have a choice but to be a mathematician and end up in computing. That was the path for that time, that era.
Yeah. Yeah, that's true. And yeah, if I'd have been born, 50 years earlier, yeah, I would have just been a pure mathematician.
You probably would have gone into maths, right? Like that's you don't really have a choice. It's like if you like that purity of problem solving, that's pretty much the only place it lives.
When I was in college and taking a computer science course, the computer teacher said, you kind of got to love math to get into it. And she couldn't have been more wrong. I mean, the right brain programming ideas were booming in the 90s. And she was just out of touch. It wasn't all Fortran and calculus programming and stuff. It was, we were talking about business logic and we were talking about language and all of these things that computers could do. So I got into it from a right brain. Obviously music is like, music and computers sort of grew in my brain at the same time. And, so it's fascinating to me to find a species from the other side of the world, the left brain approach, because, that's completely opposite to my experience. So, and I don't know about the rest of the, people out here, but the hardcore engineers that write operating systems and stuff and write, serious stuff with computer science degrees, they're certainly more into the maths. But, and guys like you, obviously, who really carefully thought about how these mathematical models play out in software.
Yeah. Isn't this a wonderful industry? I mean,
it
so
is.
Much diversity. There's room for all types of thought.
Absolutely.
Yeah. And they address different parts of the problem space. Like it's not like any of us is running out of work. There's lots and lots to do. But, the idea that you have to love math to be involved in computing is just no longer correct.
Yeah.
There are elements of computing that certainly are well served by math. But look, there are good tree negotiation strategies. There are APIs now. You don't need to write one.
Oh, yeah, absolutely.
Like you're good.
I still think that in order to do just basic stuff, especially any kind of UI, you kind of need to know a few things. You need to know ratios. You need to know, algebra a little bit. But that's about it. Maybe a little trigonometry. I was working on some Connect stuff and I needed some trig, and that was mind blowing.
Yeah, and I think there's a difference between the subjects of math that we just talked about, trigonometry and algebra, and even some calculus. But then there's also the mathematical thinking, this logical way of thinking. So one thing I like to say when people ask, well, do you have to be good at math in order to program? And it's like, no, math and programming, they're completely different operations. In math, you're taking symbols and you're manipulating these abstract concepts in order to come up with a solution. Whereas in programming, you're taking symbols and manipulating these abstract concepts in order to come up with a solution. Completely different things.
Yeah, just the shape of the symbols. Well, and really, who's the compiler here today?
Exactly.
That's the difference.
Yeah. So I like to think it's not that you have to be good at math in order to be a good programmer. It's that if you're a good programmer, you're good at math. You just didn't realize it.
Right. Yeah.
Yeah. If you learn learn the rules of symbolic math, you'll find you're already thinking that way.
Right.
Mm-hmm.
Yeah.
So where's the immutable part come into?
Yeah. So it turns out that one of the best CRDTs, is a directed acyclic graph of immutable records. So.
And one more time, CRDT, just one more time.
CRDT acronym is a conflict-free replicated data type.
Okay.
So by a data type, we mean a data structure plus operations.
Mm-hmm.
So just like a linked list.
A class,
it's a data structure,
if you will.
But it's also got some operations. And so that combination makes it a data type that's useful. So a conflict-free replicated data type is a data type, some structure and some operations that live on different replicas, different nodes. And it's conflict-free because as you perform those operations, you will never get this CRDT to be in a state of conflict on two different nodes.
In other words, no dependencies?
It's pretty cool. We can actually tie this right back to, the best implementation of an immutable CRDT that just about everybody listening to the show should be familiar with, and that is Git.
Okay.
In Git, you make a change, you create a commit. A commit is an immutable record of the change that you just made.
Right.
And part of that record is who made it, when, what was the commit comment, what are the contents of the commit, but also what is the identity of the prior commit. And then Git will take all that together, put that into a data structure, compute the SHA-256 hash of it, and say, okay, that's the identity of this commit.
Right.
Now you create another one. Okay, collects all that information, and then what is the identity of the previous one? What's the previous SHA?
I got it.
And so by creating that reference from one record back to the previous one, you're creating a directed acyclic graph. So it's directed, it's always pointing back to the past.
Right.
Here's the prior commit, here's the prior commit. And it's acyclic because there's no way for you to make a commit that will then refer to something that loops back around and points back to itself.
Yeah. So, sort of the journal pattern.
Yeah.
There, if you will. Yeah.
Yeah, exactly. Yeah. So I would call Git an example of an immutable architecture.
Mm-hmm.
There are a few other examples of immutable architectures. So some are very similar to Git, like blockchain. In that you collect a bunch of transactions, you have the hash of the previous block and you compute its hash, and now that's the reference to the new one.
Right.
The difference is that blockchain requires proof of work in order to make sure that chain never forks. Whereas Git, forks are a feature, not a bug.
Yeah.
So we call them branches, and that's how we do work.
But the main thing here is no information is ever destroyed, right? It's immutable. Yeah. It's always there.
Exactly.
I mean, we've advocated for this in databases for the longest time, is these sort of insert-only tables, the journal-style tables, because we want, like a bank, we want a record of every motion of money.
Mm-hmm. Every change.
Even if the sums come later, right? And more important is just the motion.
Yeah, exactly. Exactly. Yeah, you need that immutable history.
Yeah.
Except then when you go to do a report,
So an immutable architecture is one where data is never destroyed.
Right. Right.
not great for
And-
reporting.
Nope, not great for reporting at all. Yeah, use something else for that.
Yeah.
But yeah, another example that people might already be familiar with is event sourcing.
Yeah.
So that is a third immutable architecture, I would say, in that list. That basically there has to be some stream that puts those events into a sequence, or at least in a piecewise sequence. So for this particular aggregate, these are the sequence of events that have occurred, and now from that you can compute the current state.
Right.
And so a lot of people build applications using event sourcing. In my book, The Art of Immutable Architecture, I introduce a fourth immutable architecture that I call historical modeling. That is also suitable for building applications, but has some of the advantages of Git, as compared to things like event sourcing.
Mm-hmm.
Okay. So your product, Janaga, did I say it right?
Yes.
Okay.
Perfect.
So you said this is sort of, it kind of sounds like an actor model pattern for mobile, but not really, because an actor model has like these actors, in memory on a server somewhere that represent a client.
Yeah.
Isn't that right? So this is a little bit different, isn't it?
Yeah, it is a bit different. And another significant difference is that with the actor model, the actors have mutable state. So
Right.
you send a message to an actor, it can load its state, mutate it, save it back, and tell you what the answer is.
Right.
Whereas with an immutable architecture, mutation forbidden.
Right.
Right. Just not a thing.
You must love F#.
I actually do, yeah. I don't get a chance to program it very much. But now that that .NET has records,
Yeah.
it's like, oh man, I'm all over those records.
Yeah.
So yeah, the new version of Janaga that I'm working on right now, Janaga.net, is taking full advantage of those immutable records.
Yeah.
Yeah.
Yeah, they're cool.
Wait till you see how the code looks. It's amazing.
That's very cool.
Does the enthusiasm for this, I mean, to me, as a guy who's usually worked on performance problems, what I like about all these immutable architectures is they perform very well because they avoid contention, which is usually your performance problem. I mean, is that a reason to do it? Like, why else would you want immutable architectures?
Yeah, contention, that's really close to that idea of conflict free.
Right.
So yeah, if you have two nodes that need to kind of battle it out in order to figure out what the current state is. So you've got that Paxos kind of thing happening. Then you're going to waste a bunch of cycles in order to resolve those conflicts.
Yep.
But yeah, if you have a data structure that proves that you will not have conflicts, even if you are on just a mobile phone and you're disconnected from the network for any period of time, when you finally do reconnect, there will be no conflicts. Then you don't have to waste time resolving those conflicts. And while you're disconnected, the user is interacting directly with that device. They're not waiting on any connection to the network. So yeah, it gives you some performance benefits,
Right.
As well as that scalability.
And is this product an open source product? Does it work on all .NET platforms? What's the story there?
Yeah, this is an open source project. It is currently primarily in JavaScript. Janaga.net is the newest incantation of it. But Janaga.js is for the client and for the server. So there's a npm install Janaga, and there's npm install Janaga-server. So when you run it on the server, that's to be run as an Express node application, and it gives you some endpoints then that give you access to its internal replicator, and then you install Janaga as a client in your React application or React Native, and then that connects to that replicator, and Janaga.js on the client can also use the WebDB or IndexedDB for the web in order to support progressive web apps. So you can go offline with your PWA.
I did some work with IndexedDB last year, and I was really impressed. But I was using a wrapper for Blazor around it, which turned out to be great because, man, that's hairy stuff if you're going to deal with it in JavaScript. More power to you, my friend. That's some hairy code.
Yeah.
Ooh.
Yeah. Well, I'm aiming toward that place where, as a developer, you just have to write the specification.
Yeah.
And then let the language, let the platform figure out the behavior. So when you're doing a lot of disconnected mobile apps, you're thinking about, I'm in connected mode. I'm in disconnected mode. I have code that writes to the local database. I have code that talks to the API. I have code that synchronizes things together. Yeah. And so you're doing a lot of that bookkeeping yourself as a programmer.
Right.
But in Janaga, what I'm going for is a place where you can say, here's a fact. The user just did this thing. They entered some stuff into a form and press save. Record that fact. That's just a JavaScript object.
Yeah.
And then here's a specification which says, look for facts of this particular shape where these other related facts exist or do not exist.
Yeah.
So you write this pretty much this mathematical specification for what it is you're looking for, and then give me a projection. Turn that into a thing that I could just bind to the screen.
Yeah.
Mm-hmm.
And then let the runtime figure out how to save that to the local store, how to talk to the server, how to synchronize those data sets.
Awesome.
Yeah, that's pretty cool.
And I'm going to interrupt for one moment for this very important message. And we're back. It's .NET Rocks. I'm Richard Campbell. That's Carl Franklin.
Hey.
Talking to our friend Michael Perry. Late of the tablet show. Very late, because I think we did the last tablet show in 2014.
The website doesn't even come up anymore.
And the moment the website has come up, who knows if maybe we can...
At the moment,
turn it static. There's always archive.org.
Yeah.
Maybe I'll pull it up that way.
And it's still apparently on where all the podcasts are. So
yeah, and the podcast engines are still got it. But we're talking a bit about immutable architectures. And I sort of get this. Where does CQRS come into play? And I guess I'll define the acronym: Command Query Responsibility Segregation. Because now that you know the words, it makes way more sense. Command Query Responsibility Segregation.
I can boil it down. Tell me how, and this is purely from memory. Basically, you have one data source for querying and another data source for writing. Is that it?
That's one way of implementing it. Yeah. It's not necessarily that.
Okay.
As Udi Dahan and Greg Young would point out, that's not necessarily.
Yeah, sure.
But that's one. That's one good way.
That's the general gist that I learned.
Yeah. Mm-hmm.
That when you write to a data source, that has eventual consistency to the second database or data source that you query from.
Right.
Mm-hmm. Yeah, that is the most common way of doing things, and it makes a lot of sense. Like you were just saying, you wouldn't want to run reports off of an immutable history of records. That's not what that's for. So use something else for that, and that's precisely what CQRS means to me. Is that you're going to have something that's really good for those reports for that read side. That's your projections.
Yeah.
So run your reads from your projections. And then your writes, you're sending those into some transactional system. And if that transactional system happens to be a directed acyclic graph of immutable records, hey, you're golden.
Yeah.
I hear you got event sourcing on your event sourcing, so I got you event sourcing.
Mr. Subliminal, event sourcing, every other word, event sourcing. You want some chewing gum? Event sourcing.
But I do appreciate the idea of optimize the ingress path and optimize the outgress path separately.
Right.
Mm-hmm.
Right? That there's an ingress path for orders to be entered, and then there is that one of the output paths is fulfillment, but another one is reporting. Mm-hmm. They don't have to be. Why do everything in one place and basically have suboptimal versions of all of it?
Right.
Right. Exactly. Yeah. Yeah. So now imagine that you could just write a specification. What does your reporting database look like?
Yeah.
And then, computer. You figure out, okay, whenever this event happens, go update that table.
Right.
Yeah, that's computation. That's machine's job, not mine.
Yeah, you could solve that. But this is where you get into that sort of relationship mapping thing. It says, this is what the incoming stream looks like. Maybe it's blobs, it doesn't really matter, whatever it comes to, and it maps it out asynchronously. The transaction's already been received, but asynchronously now distributes it to various sources that care for it.
Yeah. Yeah.
Oh, and you got to have a queue in there somewhere, or at least one.
Yeah. That's okay. Wow. That is, so I want to kind of tie this back to, what we were just talking about with event sourcing. I do offer an alternative to event sourcing as a different immutable architecture that I call historical modeling. Whereas event sourcing is this at least piecewise, linear set of events. A historical model, they don't have to be linear. They don't have to have occurred in a specific order.
It's not tied to the data per se. It's tied to the
Let me see if I can give a practical example. So you place an order as a customer. And then what's the next thing that's probably going to happen? Well, the shipping department is going to pick that up and they're going to create a pick list. But also the accounting department is going to pick that up and they're going to create an invoice.
Yep.
So the pick list and the invoice are both historical facts. They happen. They are decisions that somebody made based on that order. So if you model that as a tree, you'll see here's the order at the top, and then the pick list and the invoice are two leaves of that tree, both pointing up to that common root. So it makes a little triangle.
Yeah. I would argue the pick list is fulfillment. Shipping is another task again. Mm-hmm. That you end up with this series of artifacts related to the order. And they're all done by different people. Sometimes they're sequential. You need to be picked before you can ship. And in theory, you shouldn't invoice until you ship. But
But the tree architecture sounds like handles that however you want to branch it.
Yeah, exactly. Yeah, so shipment is another historical fact that points back to the pick list.
Yeah.
But the shipment doesn't care about the invoice.
No.
So it's just pointing up to the pick list.
Yeah.
There's there's an accounts receivable, which is actually just a report that you run from invoices. So the accounts receivable itself is not a new fact, but the payment
is another element.
Is another fact.
Oh, yeah.
And that points to the invoice, but the payment doesn't point to the shipment or to the pick list. So you've got this tree, this graph that branches. And
now do a partial return or a warranty replacement. And you can tell the architects in the room because you get all really excited. Right, this is good whiteboard stuff, right?
Absolutely.
You start drawing that out.
Tree for you.
Yeah, but you're looking for those dependencies and what they're related to and where we can make them execute independently. Like these are also unique units of work for development too.
Yeah.
Right?
Yeah, exactly.
This is it's always that question of how do I get 6 people to work on this? It's like, well, because you peel out the one piece, the payment engine, and that goes to one person, maybe 2, if you're doing a little pair programming or want 2 sets of eyes on things. And then others are on other pieces. Like you have these, areas of concern that have discrete interfaces on them that allow you to parallelize development.
Right. Exactly. Yeah. And so
this is the same reason I ship 2 copies of Mythical Mammoth to every manager so they can read it twice as fast.
And I'm going to read Michael's mind here. He's saying, well, what I would do is I would write the engine and then have one guy write the spec for everything. And then the engine does it all. Right?
Yes. And
that's what we want.
Yeah. And the person who writes the engine doesn't even know about your problem
domain.
Doesn't
care.
He wrote the engine and he's long gone.
No, he's got a problem factory somewhere.
Exactly.
Oh, one of my favorite jokes.
All right, these are a whole bunch of insider architect jokes. I'm pretty sure we're making fun of ourselves.
I had a problem, so I used Java. Now I have a problem factory.
That's an old joke, but a good one. Yeah. And you have to say it slower than that because, Java.
Yeah, right.
All right. I shouldn't make fun of Java. Those guys do good work and they're more like us than different.
That's true.
It's not fair at all. And no reason to be mean to them. They have Oracle for that.
Oh, man. man.
How much time do you spend doing architecture then, Michael? I mean, you work for an agile practice group, right?
Yeah. I work for Improving, and so we offer consulting, agile training, and so my role at Improving is to help other improvers grow their careers, and also, by the way, bill clients. So I'm often running a team at a client. So in addition to helping to grow that team, I'm in charge of the architecture for the project, as well as often doing the technical lead role.
Right. Because I mean, presenting a directed acyclic graph to the average developer, they're like, where do I log in? Like it's not a product, right? It's a thinking model.
Yeah.
And then you get into questions about, well, how do I implement this? Like, is there a library that will drive me towards a DAG?
I don't start people there.
Okay.
Yeah. So I start people first with analysis. Let's use a directed acyclic graph in order to analyze the problem. And that uncovers all sorts of edge cases, but then also gives you a way to document them. So you say, okay, like the returns that you were just talking about.
Yeah. So the breakdown in Giggles we just had was actually us working through the graph of a retail workflow or an e-commerce workflow.
Right.
Which, I mean, I've done so many times I don't even laugh about it anymore.
Yeah.
Right. It's just like, the number of times we figured out, are we going to do back ordering? How do we do returns? Do we do Unify where you can deliver back to the store? Like, and just drawing out those diagrams. Like, I think you forget how weird it is.
Yeah.
To think about business processes that way.
Yeah. And a lot of times people will draw those diagrams as flowcharts or as state transition diagrams, or the more modern equivalent, draw those as a sequence of events. Do some event storming,
right?
But the diagram that I propose is one where you've got an ellipse that represents one historical fact, one decision.
Right.
And then it's got arrows pointing up to the predecessors, those decisions that had to have come before.
Right.
And so now you can walk this tree or this graph really in any order as long as it's, from the past to the future, from the top down.
Right.
So you have to follow those arrows backwards. I like to run my arrows backwards, but yeah, you can take any of those paths at any time, and you can describe all sorts of different scenarios with that same graph. So it ends up being a lot cleaner, a lot easier to understand than a flowchart or a state machine that does the same thing.
Yeah, I do appreciate that it's more representative of the problem space ultimately. To sort of you're really organizing by artifact.
Yeah. Exactly. And so then once I've got people thinking in terms of a directed acyclic graph to analyze the problem, then we can start talking about how do you implement based on this. And even for that, I don't jump to, hey, let's use Janaga. Instead, I say, all right, you're used to relational databases. Relational databases have foreign keys. A foreign key is a reference to another record. So what if every record was an immutable historical fact, and those foreign keys were the pointers to your predecessors? Let's actually build a database like that. I've done a number of systems that way, and it's really really powerful.
What about structures in data? Like I'm thinking of lists of objects of things. If you were to use immutable architecture, where you have records, now you've got duplicate records that, no, this is the current one and these are the historical ones. That could get hairy, couldn't it?
Oh yeah, that's a really fun problem. There's a pattern that I go through in the book called the mutable property pattern. Wait, you just said immutable.
Wait,
you call this
is it immutable? Yeah.
Immutable property? What's that?
He broke his own rules.
Yeah. So this is a
what
way
do all
that
the other farmers on Tatooine think of you? Because
yeah, this isn't right. But yeah, the idea is that you are going to simulate mutability using immutable records. And so the way that I simulate a mutable property is that, I've got a historical fact that says the value of this property is this value, and the prior value, the one that I just replaced, is that one. So the predecessor, the pointer to the other fact, is the previous version of that property. Now, what's really cool about this is if you think about this not in terms of a sequence, but in terms of a graph, you can have concurrent changes to a property. You can have somebody editing a property on their cell phone, somebody else on the website, and you both create these facts that point back to the same prior version.
Right.
And so you've created a tree.
You're okay with a tree then, that two facts could be pointing back to the same historical fact?
Yes, Ooh. Exactly.
You are crazy, Mr. Perry.
But yeah, you're used to that as well in Git.
Is your milk blue? I'm just curious. No, all right. So this is how strings work, isn't it? Inherently, how strings are immutable objects that when you say, my string variable equals this and then equals this plus that, you're actually creating a new string that from this plus that. And the string that just had this in it is gone. It's marked for death. It's unusable memory now.
It's freed memory.
Yeah. So
it's not immediately freed. It will be.
Yeah,
freed.
It is immutable. So you've got that part. The thing that strings don't do is keep track of what was the previous string in this variable.
Right.
Yeah, you can't undo a string, for example.
Yeah, but
string.undo.
Yeah, taking it back to Git, it's perfectly fine to have two different commits that point back to the previous commit. You've just created a branch.
All perfectly fine until you try and merge. then nobody's fine.
Or you try to do a link query to find some records in your record list.
Yeah. Oh, okay. Yeah, let's put a pin in the link query one.
Okay,
good. That's really cool. But merge, I would want to talk about this. So in CRDTs, one of those operations that this data structure needs to perform is a merge operation, but it's not the same as a Git merge. Git is a CRDT. So if you were to fetch from a remote, now you're performing a merge. You're taking information in that remote and you're merging that information into your own directed acyclic graph on your repository.
Right.
Actually performing a Git merge creates a new commit. So that is an actual change. That's an update. That's creating a new historical record. And now that you've created that, you can push, which is a merge in the opposite direction. So the thing that we call merge in Git, which is so painful, is actually not a merge. And the thing that we call a merge conflict in Git is not a conflict in the term of in the CRDT world, because as a CRDT, it should be conflict free.
Right.
Right.
What's actually happening is the interpretation of what this history means now has been called into question because you've got concurrent edits. And that's exactly what's happening when you've got these mutable properties that two people change at the same time. Now you're calling into question, what does that mean?
Yeah.
And the data structure itself is not in conflict. It's got a graph that has two leaves on it. That's perfectly fine. Mm-hmm. But now your interpretation of it is where you say, oh, was it this phone number or that phone number? Which one is it? And then the way I like to do that is to allow a human, just like in Git, to resolve that conflict, to make the decision which is the correct phone number, and then create a brand new historical fact that points to both of them. Just like in Git, when you do a merge commit, it points to both of its parents.
So was looking at Git for you the sort of impetus of this pattern that you're describing? I mean, you seem to be referring to Git a lot. Or was it like, oh, Git does this thing that's in my brain? How fortuitous.
Yeah, it was a little bit more of the latter, because I first had this idea of kind of paying attention to the history rather than the current state around 2001. And I wasn't familiar with Git if it was around at that time.
No, I don't think so.
Yeah, but yeah, then I kind of started to evolve this, and then I saw, oh, there's event sourcing. Oh, that's also paying attention to the history and not the current state, but in a different way. Interesting. that feels about right. Oh, here's Git. Oh, that's doing this thing in a much more familiar way.
Right.
But just for source code, whereas I want to do this for
everything.
Applications in general.
Yeah.
Oh, that's it. So
No,
yeah,
not
a lot
again.
of things that all kind of felt familiar were all happening at the same time.
All right. Well, wow, that's really cool. So I just one more question before we go. When you go out on a clear night and you look up at the sky, do you see 2 full moons?
Uncle Owen, this R2 unit's got a bad motivator.
No, seriously, this is mind-blowing stuff. And just to be able to think this way and apply it to common things that you use in everyday life, and how could it make things better?
Yeah,
I love that.
Yeah, it is amazing when I'm able to bring a development team along with me, and we use this as the way of thinking about a product, about the way that we develop the product.
Yeah.
It really comes up with something much better than we could have done without it.
What's the name of the book again?
The book is called The Art of Immutable Architecture.
Excellent. And you can get it wherever fine books are sold, I take it?
Yes. You can go to immutablearchitecture.com. That'll give you a link directly to it.
Do you have an Audible version?
I do not yet have an Audible version, but yeah, that would be a great idea.
Well, don't ask me to read it, because I will screw it all up. I'll be like,
nobody expects all the
this?
WTFs in it,
I will read it, however. So yeah, this is great stuff, Michael. Thanks very much for being with us today.
Thanks, Carl. Thanks, Richard.
All right. We'll see you next time on .NET Rocks. .NET Rocks is brought to you by Franklin's Net and produced by Pwop Studios, a full-service audio, video, and post-production facility located physically in New London, Connecticut, and of course in the cloud. Online at pwop.com. Visit our website at dotnetrocks.com for RSS feeds, downloads, mobile apps, comments, and access to the full archives going back to show number 1, recorded in September 2002. And make sure you check out our sponsors. They keep us in business. Now go write some code. See you next time.
Got transmitter banned by the FCC.